Alrighty. Hey, folks. I'm Mike Weber, and I'm going to be chatting with you today about ChromeAlone, which is a framework for transforming a browser, in this case specifically Chrome, into a C2 platform. And this is going to be a modified version of a talk I gave at DefCon a couple of months ago. After I gave the talk, Sharon reached out and mentioned that you guys are expanding the threat model potentially for Chrome into areas that this talk covers. And she wants to know if I'd be willing to give this talk to you guys, which is a big hell yeah for me. So without further ado, let me dive into it. Once I select my screen so I can move the slide. So I'm Mike Weber, and I've been messing around with Chrome in one form or another for a while. I gave a talk back at DerbyCon in 2018 about writing malicious Chrome extensions, and I've kind of never stopped mucking around with it since then because it's an extraordinarily effective place to abuse if you're attacking in sort of like a red team capacity. On that note, I work at a security consultancy called Praetorian Security. We do red teaming. I work on the research and development team there, where I throw together various tools to help my team get their work done. And also, I manage to move our logo directly into the middle of our slide. So it's just chilling there. No idea why that's happening. Fun fact, there are a bajillion Michael Webers in security. I am none of the Michael Webers or Mike Webers at the bottom of that slide. If you need an easy way to remember me, I work at Praetorian. We have this whole like Roman motif thing going on. I'm the right age millennial, so I love the movie Home Alone. Those are kind of the easy things to remember me by. And this is a pretty condensed talk. I'm going to try to shoot for 40 minutes, so we've got like 20 plus minutes for questions, which will be at the end. But there's going to be a bunch of times during this talk where I'm going to essentially say, okay, and then you just, write a SOX proxy in JavaScript or something. And obviously, there's a lot more to that than, just one throwaway sentence. So if you're curious about the implementation details of that, you can go to the GitHub repository for this, which is open source, that has all of the details for it. And also, I'm happy to dive into any details specifically at the end of the presentation as well. As a reminder that I know I'm going super fast, occasionally you'll see the draw the owl meme rear its delightful head every time that this comes up. So I probably don't need to tell you guys why the browser is important and why it's targeted by attackers. From a red team perspective, it's whitelisted by everything. People need to use the browser in order to access all of the fun internal resources that an attacker is really interested in, be it Google Workspace or Office 365 or whatever is the gateway to everything that we want to get our hands on. And as an added bonus, also something you're probably well aware of, Chromium is so chock full of features. At this point, it's practically an operating system. So there's just a ton of attack surface for someone that wants to weaponize features into something a little more interesting. And specifically, the features that I'm going to be talking about weaponizing are Chrome extensions and isolated web applications. So, Chrome extensions or browser extensions. For most people, it's the thing that installs an ad blocker. You're more than well aware. It unlocks a healthy amount of capabilities within the browser, which you can use to sort of bypass certain internal security features if you ask for the right level of permissions. And, attackers have been trying to do this for quite some time. You can just go into Google and type, malicious browser extension, and you'll get a news article about some attacker that's found some way to, steal people's credentials or run a supply chain attack. I don't know. I haven't done this news check in a couple of months, but I'd be unsurprised if there was some other newsworthy browser extension run amok. It's very common. From a pen testing perspective, which is what's interesting to me, there's a series of extensions out there which are useful for pivoting into somebody's network. So I'll choose Curse Chrome to talk about here. It's a really cool extension that lets you steal cookies right out of the browser and then force all of your HTTP traffic from that person's network position, which is a great way to get around a lot of restrictions for controlled access to resources and whatnot. And once again, I know your team is well aware of this, and you've been working to reduce what extensions are capable of. So there was the whole manifest v3 change, which at this point has happened many years ago, which removed a couple of really fun features I used to take advantage of for stealing cookies. And so very sad times for me, but in general, the users are safer for it. The Chrome Store review process as well, which is one of the main ways that you can distribute extensions to everyone, has become much more intensive. You need to write an essay now every time you ask for one of these dangerous permissions that I'm talking about. And then one of the things that made me really sad was there used to be this super cool like extension adjacent thing called Chrome Apps, which had really neat capabilities from an attacker's perspective. And almost immediately after I gave my talk at DerbyCon back in the day, they got deprecated and ripped out of the system. I mean, it was a very slow deprecation, but they're gone. They're gone forever, except they're not gone forever. They have come back from the dead in a beautiful way in the form of isolated web apps. And isolated web apps, I'm going to steal something from a presentation that some folks possibly in this room right now gave at ClickOn 19. They exist because when you want to add a new web API into Chrome, there's a bunch of design principles that you need to stick to. Two specific ones are, it should always be safe to visit a web page if you add an API to Chrome, and users should always be asked for meaningful consent for anything that might be questionable. And, you know, of course, in consulting, we have the phrase, client's going to client, and I'm sure you guys have customers going to customer. Inevitably, someone will try to ask for an API that violates one of these two things. And that's one of the reasons that isolated web apps exist now. And so from my perspective, when you want to do something really dangerous with Chrome, you can use an isolated web app. And so some of the permissions that exist within isolated web apps are things like direct sockets, so that Chrome app capability is right back in the browser again, getting access to some of the more dangerous parts of web USB, or specifically get all screens media. This is one of the more compelling use cases for IWAs, in my opinion. So say that you're a testing center and you want to make sure that nobody is, using your machines to secretly open another window and run like ChatGPT or something and cheat on your test. You want the ability to view every single screen and every monitor and see what's going on to make sure that's not happening. But simultaneously, you don't want to ask the user permission, because a cheater will just say, no, I don't give you permission to look at my screen. So there's this API now which says, hey, I'm going to get to look at all of your screens. I already have permission. I don't need to ask the user, and it just happens. And understandably, if you're going to have these, you need to lock down these sorts of dangerous features behind some additional controls. So isolated web apps have an entire bundling and signing process to make sure that every asset that's running has been verified. And at the moment, this is more of a potential control, because you can just self-sign an isolated web app and install it. But I know that the capability is baked in, that you could say, I only trust a key from Google. We can only install Google isolated web apps or whatever. There's a very strict content security policy that stops people from essentially smuggling in additional code that might look suspicious. And even when this presentation was given, there was a sort of asterisk on, hey, well, apps could just embed an entire JavaScript interpreter and bypass CSP. There's other ways to do that, which we'll get into in a little bit. And then, of course, isolated web apps have that whole isolated part where you're not able to interact with the rest of the browser in theory. Mainly, you can't interact with cookies. You can't interact with any existing sessions. It's kind of in its own thing. And to drill a little bit more into that content security policy, I don't know how many of you just know content security policy off the top of your head. This is fairly locked down. There's not a lot of wiggle room for sort of arbitrary evaluation, except for this use of WASM unsafe eval, which I'm going to talk more about that later in the presentation. But essentially, WebAssembly has very poor granularity for specifying what you can run, because it's essentially, arbitrary code execution within the WASM sandbox. So there's really not a lot you can do, but it opens room for a lot of fun stuff. And in that same presentation, there were some quotes from the developers, some of whom may be on this call, which largely acknowledge, hey, if you want to use isolated web apps to do bad stuff, you can. There's not, it's no different from Chrome apps, where if you wrote a malicious Chrome app, you could do something particularly bad. There was one statement that somebody made, which is, it was meant as a joke to open up as like, well, who's going to use this besides malware authors? Because, testing centers and other legitimate use cases. But, as a malware author, I think this is a super cool capability. And I'm going to walk through some of the ways we're going to have some fun with that. And the way that I'm going to walk through it is kind of a case study where, let's come up with a sort of nightmare red teaming scenario where I'm trying to hit an organization and steal all their secrets. So I'm going to say that this organization uses a single sign-on provider like Okta. That could be Google Workspace, but Okta is what I've got my demo for. They're going to use web authentication. So they've got some sort of YubiKey or Titan key, which is necessary to access specific resources. They've got great secrets management. No amount of read teaming in the world is going to get the secrets that we need to win. It's all stored in this case, I'll say HashiCorp Vault, but replace that with your secret storage manager of choice. And then, of course, they've got great endpoint detection and response that's really dialed in, so we can't just do standard, infect a machine pivot, and so on. So specifically, I'm going to be talking about a user that they log into single sign-on once a day using Chrome. They never log into that secrets management system, but the Vault secret management system has the information we need to RDP into our final target. And of course, even if they did log into it, they would use their Titan key or MFA key in order to access it. And so that's a pretty tough set of restrictions to get around. So now I'm going to rig this for me, the attacker, which is, here's the assumptions that we're also making as a part of this. One is we're able to trick the user into running a PowerShell script on their Windows host. The installation is sort of a post-exploitation mechanism, and I recognize that this is outside the conventional threat model for Chrome. I know that's changing, but for a long time, it's been assumed if you have RCE on the box, there's not a lot that Chrome is going to do to stop you from doing what you're going to do. Outside of that PowerShell script, of course, we can assume EDR is fine-tuned, the SOC knows what they're doing, and of course, Chrome has to have the ability to access all of these resources. It's not firewall. And I'm sure you're all probably going to have to squint in order to have any idea what's happening here, but this is a rough architecture diagram of the approach we're going to take. I'm terrible at drawing these things. This does not communicate information in any way or form, I know. The only things that you need to take away from this diagram are, one, we're running 2 instances of Chrome on the target's host. One is their original default installation, and that's where we're sideloading a Chrome extension into it. And the other one is there's sort of a second profile, which we're going to sideload an isolated web app into. And we're going to hide that second instance using some features in Windows that let you display stuff on a separate desktop the user can't see. And I personally think this isn't the right way to think about how to approach the problem. I'm a fan of Home Alone. I'm more a fan of thinking that we have a plan to turn the resources that we already have, our normal default behaviors, into something a little more dangerous, and then use that as a mechanism for making our way to our target. So specifically, we're going to sideload a Chrome extension and an isolated web app, and then we're going to use that extension to capture single sign-on credentials, and then we're going to use the isolated web app to tunnel traffic through the user as a SOX proxy. Then we're going to switch back to the extension and trick the user into authenticating to Vault. And then we're going to switch back one more time to the isolated web app and RDP into the target via SOX. And I know this is a fairly extensive plan, but we'll walk through each step. So to start with, in the world of Chrome extensions, the default configuration is all stored on disk in JSON. It's in a preferences or a secure preferences folder. You just list all of the permissions that your extension needs, and then provide the details necessary so Chrome knows where to load it from, and then you're good to go. And it's very common for extensions to ask for all kinds of dangerous permissions. This is very similar to what we're ultimately going to ask for. And this is Adobe Acrobat. This isn't like malware. This is just a pretty conventional use case for Chrome extensions. When it comes to actually overwriting them, There are protections built into the browser, and there have been for a long time, where there are these sort of security hashes embedded, where you sort of use a specific algorithm to hash the extension and then say, hey, if someone changes something and doesn't update this hash, then you have a problem. And I know for a fact that this is no longer the only protection. These hashes here aren't just an algorithm you can go look up. They also use a sort of like app-bound key, similar to how cookies are encrypted in Chrome. I know that's been rolled out. That being said, since it's been rolled out, I have not seen that stop me from sideloading anything in an enterprise environment. I believe the rollout for that feature is a little more slow in domain-joined environments or enterprise environments, mainly because, you can't just make a change and then break every enterprise across the across the country. But that's the nature of the beast. So the reality is the sideloading stuff I'm going to talk about is still relevant, at least for some period of time. And it's been relevant since like 2016. There's been malicious actors doing this. But more recently, some pen testers, specifically Nicholas Murray and Gordon Long, have published code that lets you calculate all of these hashes and then sideload a Chrome extension manually without ever interacting with Chrome directly. And that's just editing a couple of files on disk. Separately, I know Gordon Long has some additional research that he's going to talk about. At question time, I might dig into this, but I'm not going to blow up his spot while being recorded here. And of course, because we are able to set any permissions we want when we sideload these extensions, we're going to ask for literally every possible setting in Chrome we can. So we're going to make sure our extension runs in incognito mode and we have access to file URLs so we can build out like a file browser and all kinds of crazy stuff. But that just kind of goes without saying. More interestingly, isolated web apps are very new. So no one's written anything with regards to how you sideload these things. And sadly, it's not just a JSON file on disk. It uses the synced data level DB store within the browser, which is interesting. So if you go and enable isolated web applications within Chrome, and then you sideload it and you try to see what's actually changed on disk, you'll see the only thing that gets touched is that level DB log file. Which, when I first saw that, I was like, oh, .log, that's surely a text file. No, it's not. It's definitely not JSON. It's a Google DB tool for, essentially, from my perspective, a key value store. And level DB is so much more than that. But from the attacker perspective, it's a key which says web_apps-dt and then value, which is based off of the public key that's used to sign your isolated web app, and then a giant byte array, which is like a 7-byte header, and then some blob which describes the isolated web app. The header is very simple. It's a CRC32 of the block data, the length of the block data, and a block type, which would matter if we were using the more advanced features of level DB. But since we launch a completely fresh version of Chrome to sideload into, we just say it's a full block because the database is otherwise empty. And of course, it uses CRC32C. I didn't even know there were multiple forms of CRC32 when I started on this project, but it's all open source. You can pull that code, implement your own CRC32 hash, and then inject into level DB. The actual binary content that's beyond the header is another Google classic, which I'm sure many of you, if not all of you, are very familiar with, which is protobuf. Essentially a way to define serialization of objects into binary data. And web applications have their own protobuf object, which just defines all of the metadata that matters, like where it's installed, how it was installed. You can even say, like, was it installed by the user? Was it installed by policy? Is it a system isolated web application, which means it'll just be loaded anyways and you can't uninstall it. Like, these are very helpful things to be able to set to whatever we want. So essentially, in a nutshell, the sideloading process is you define the application that you're interested in, our malicious application. We serialize it into a protobuf object, calculate the CRC32C hash for it, inject that into the sync data level DB structure. We also need to turn on some feature flags because isolated web apps aren't technically enabled by default. but you change a JSON file in local state and you're fine. And then you also need to calculate the isolated web app ID that's based off the public key. You have to run the isolated web app from the command line. And then you also need to run it without showing the user. That's that hidden desktop thing I mentioned in Windows. On Mac OS, you can just run it using Launchpad or Launch Control with a flag to not show the window. So that's it. That's all you need to do. I know that that is an incomplete way to describe how you actually sideload these things. But if I went into detail on all of this, we wouldn't have a rest of the presentation. We would just be here all day. So if you have any questions, please throw them at me afterwards. But for now, we're going to move forward, because if you need to see an example of that within that GitHub repo I posted earlier, it's implemented in the Doorknob project. And Doorknob is a series of PowerShell scripts and now Bash scripts to allow sideloading Chrome extensions and IWAs on Windows and Mac OS. And ideally, the user barely sees anything. If that script runs, they'll see Chrome flash or flicker. Besides that, they have no idea that there's now 2 versions of Chrome running with the isolated web app and Chrome extension. So we've covered our sideloading process. The next step is we need to extract those credentials so we can pivot deeper into the infrastructure. And this is something that Chrome extensions are fine for. Chrome extensions, we can ask for permissions to capture like the clipboard. We can ask for permissions to copy all the cookies. We can ask for permissions to read the user's history. That's enough for us to be able to get the credentials that we're going to need. You used to be able to just say, hey, I'd like to intercept every single request you make using the web request blocking permission. That's dead now, sadly. But we can instead use content scripts to just inject into every single tab, and then we'll just use JavaScript to do that. We essentially give ourselves universal cross-site scripting in the browser, and we then use that to hijack every single login request and steal their credentials. And there's several security mechanisms in place, which are sort of like they build these different boundaries, these worlds, if you will, to stop like your background scripts from communicating as directly with your content scripts, from communicating with, isolated web apps. But the general plan here is we're just going to install JavaScript into literally every place we can, and then use a combination of the message sending APIs and WebSockets to build a kind of like microservices nightmare that lets every piece of Chrome communicate with every other piece of Chrome, and then we pull down all these barriers and we win. And a generous user or security person might say, well, won't the user notice that there's JavaScript running everywhere? And I mean, that's always happening, so I kind of doubt it. But even if that were the case, we can also use those WASM unsafe eval permissions to just obfuscate the hell out of everything. So all of these interceptions we're doing, they don't have to be through JavaScript. They can be instead buried in this giant binary blob that Chrome does not provide good introspection for. And this isn't just like, it's not like, oh, well, Chrome is bad at it, but other things are. Everything is bad at introspecting on WebAssembly, especially if you compile it using Go or Rust, because then the entire runtime for Go and Rust gets baked into these things. So you've got these 5 or 10 megabyte WebAssembly blobs that just are black boxes and nobody knows what's happening inside them. And because WASM unsafe eval isn't a granular permission, if WebAssembly is allowed, you immediately can perform these kinds of things. And the final piece of the puzzle, this is kind of how we replace eval, is you can use WebAssembly to call back out to JavaScript to trigger the loading of another WebAssembly stream. So you build out this kind of like, Matryoshka doll of a WebAssembly which contains more WebAssembly, but calls out to JavaScript to load that WebAssembly, and then that calls out to JavaScript to load more WebAssembly. And you can also push WebAssembly blobs down over the internet. There's a lot of room to essentially, eval is back in style. So we have eval in every single tab now. And if you're curious what that looks like, because some of you might not have coded WebAssembly before, in JavaScript, it's a couple of lines to load WebAssembly. WebAssembly via Go, there's a interop library you can use to call out and then invoke essentially exactly that same JavaScript. And it's more verbose. That's a little longer, but you can replicate like, you know, most capabilities here. And actually, just the other day, I actually realized that you can use the internal HTTP client of Go to then interface with the direct sockets API, and you can just make raw. You can do like domain fronting and all kinds of conventional Go web client attacks through the browser this way. It's pretty cool. In general, the Chrome store review process, which I know isn't really, you know, this is a different part of the org. It's not you guys, but like the process for making sure that an extension, or I mean, eventually, presumably an isolated web app, is safe is borked, because they're going to take one look and see a giant WebAssembly blob, have no idea what's happening, and then, you know, they flip a coin or, you know, consult a horoscope and decide whether or not to accept it or not. But we've successfully gotten several malicious Chrome extensions into the store without any issue, and I know that we're not alone in that. So, anyways, we've pushed all of this stuff in. What do we actually do with it? And that's where that universal cross-site scripting mechanism that I'm talking about kind of comes back into play. So essentially, we just add event listeners to every single form that we find to capture any credentials. And we can also man in the middle any relevant functions. So like, you know, if we're calling out to web authentication, when you want to click a YubiKey or something, we can also make sure that they call our code first. And I'll get into why that's important in a bit. But in practice, you know, it's easy to identify forms. We inject our event handler in there, and then if anyone submits anything, we have control of that in code. And, you know, in the actual extension that's on GitHub, it obviously doesn't pop up an alert window and highlight things in red. That's all silent. Additionally, sometimes you can be as clever as you want with JavaScript, but you still need to shell out. And lucky for us, there's a mechanism called native messaging, which pretty much purely exists to say, hey, Chrome, I want you to run this executable on disk. And the main security protection around that is there's an assumption that you're going to use a sort of like operating system primitive to describe, you know, how that's invoked. So you have to have edited the registry, or you have to have dumped a file on disk, which normally can't happen if you just go to the Chrome store and add something. So it's implied that native messaging only happens if you've already run an installer or something on the machine. So that's kind of why I think this is even allowed in the first place. But because we're sideloading, of course we're going to do this. We edit our registry key, or we edit our configuration file on disk, and then that points to a JSON file. That JSON file is really just a wrapper to say, hey, what am I going to run, and what extensions am I allowed to run it with? And then in practice, it ends up looking something like this. So on Windows, you'll see Chrome literally call cmd.exe and then run whatever binary you're interested in. For those with incredibly good eyesight, it ends up looking something like this. I don't believe this is subtle or stealthy. I don't think this is a problem that anyone needs to worry about, because any half reasonable EDR or SOC is going to think this is suspicious and raise flags. This is kind of more, this was a DefCon talk when I gave it. So, you know, the novelty of popping calc is important, and I threw it in here, but I don't really consider native messaging to be a security hole in Chrome in any way or form. In general, though, the the tool for this, the folder that describes all of this, is in the Hot Wheels folder, which is stored on that GitHub repository, and that covers credential jacking and shelling out and session theft and file read operations and history read access and all the goodies you really need in order to be particularly effective when you're running around somebody's network. So we've captured those SSO credentials. The next step is proxying our traffic somewhere else on their internal network. And normally for this, I would say we'll just use Cursed Chrome. That's that pen testing Chrome extension that I mentioned earlier in the presentation. It's great, but it only does HTTP. And we just spent like 10 or 15 minutes talking about how to sideload an isolated web app. So let's actually dig into that. And what we're going to do is take advantage of those direct sockets permissions that have been added. These are those Chrome apps permissions that I wanted to run with way back in the day. And if you take a look at the use case for direct sockets, you can even see it calls out like, well, this is so you can like SSH or RDP or, you know, hit like a virtual desktop infrastructure, which are all very interesting pivot points for an attack. So I wanted to use direct sockets. That was kind of the whole reason I even did this project in the first place. I did notice in the process of using this that in general, most of the isolated web app permissions do come with caveats or additional restrictions, which makes sense. Some of them I don't quite understand. So for example, like if you're trying to host a port, because you can also listen with your arbitrary sock permissions with direct sockets, that port has to be above 32,678. I don't quite know where that number comes from, but it stops us from listening on anything that, you know, in general might have a OS purpose, like, you know, like 135 on Windows or something like that. That being said, you know, we can still make arbitrary connections outwards to whatever we want, and that's more than enough. So, you know, my first pen tester idea was, well, I'll write a WebAssembly SMB client and a WebAssembly RDP client, and I'll write all these things. And then reality kicked in. I was like, well, I'll just write a SOCKS proxy and then run all of those tools on my local machine and tunnel them through the browser that way. And then I don't need to write an RDP client. And that was ultimately the smart way to do things. And that's ultimately what I did. The final problem, though, is that, you know, we have isolated web apps and they are isolated. So how do we get access to all of those other cool things that we just talked about in the Hot Wheels component that's stealing passwords and stuff? And the answer is, if we have the ability to just write arbitrary or, you know, open arbitrary sockets, we can use our isolated web app to create a WebSocket server. And then the extension can reach back out and sort of bridge our isolated web app back into the browser. This is back along that sort of microservices nightmare thing I referenced earlier. So you just write a TCP socket server, connect out to that. Now the Chrome extensions and isolated web apps work together. Then you just implement a sock server using direct sockets and JavaScript, and you're done. And obviously, there's a lot of work being hidden behind those 3 bullet points. But at the end of the day, if you need to see it, it lives in the Blowtorch repository or Blowtorch subfolder of the GitHub repository. And I called it Blowtorch because this is probably the most overkill thing that's baked into the capability, to be honest. You get a full SOCKS 5 proxy to the attacker. So all the comms from an AV perspective, they're coming from Chrome, which is normally whitelisted. You can combine that with the cookie stealing from the extensions, and then you can essentially replicate the cursed Chrome capability set, but now we can RDP into things. The final thing we need to deal with is how do we deal with MFA tokens that are physical. And originally, the reason I even picked this as part of the presentation was in 2018, when WebUSB got added, there was a way that you could talk directly to YubiKeys and then just effectively request arbitrary website keys signing without visiting the website. And then that all got locked down, and unrestricted WebUSB got announced as being added into isolated web applications. And there was even some like brouhaha, you know, in the news of like, oh my God, unrestricted WebUSB is coming for all of us. So I figured I would just try to replicate that 2018 stuff. And ultimately, I couldn't. And I don't know if that's because unrestricted WebUSB actually means unrestricted except for the things we know are dangerous, or I was using it wrong. If I had to guess, I was probably using it wrong, to be honest. But end of the day, I'd still promised that I was going to have some sort of mechanism to fish YubiKey clicks. So I got desperate and accidentally found a UI exploit within Chrome. To call this an exploit isn't really fair. Like, this isn't even a bug that's worth reporting, but this is a behavior that was interesting. So essentially, if you're in Chrome and you have the ability to just open arbitrary iframes, because remember, we've got that universal cross-site scripting. If you open an iframe on whatever web page you actually want to trigger your authentication request for, and then have a content script trigger it, you will be able to be on one website and trigger a web authentication request for a different website. Nothing super special about that. It's just unexpected. And also, you know, these URLs don't match. So, you know, a more keen-eyed user would actually notice and probably not click, or they'd know something was up. However, what happens if you have multiple tabs and trigger a web authentication request? And on newer versions of Windows where you integrate with Windows Hello, you can't do this. Windows Hello only allows one web authentication request at once. But you can launch Chrome with a flag that disables its web authentication integration, and also on Macs, they just don't even have this protection at all. And you can absolutely have multiple boxes popped up. So if you do that, when you press your UV key, which is flashing, which tab's challenge is resolved first? Is it the active tab, or is it the first tab you pressed? And because we're talking about it, it's the first tab that you've pressed. So from the user's perspective, they've just clicked their flashing Titan key and nothing happened. So they hit it again. Now it goes through. They don't realize they've actually signed 2 signatures instead of 1, including for a website that they weren't currently visiting the page for. So the extension from this is we just find an idle tab that's inactive, and we trigger that tab to open a web authentication request. The only notification the user gets is, hey, there's a little dot here that indicates there's been some sort of UI pop-up, but I don't believe that most users are going to notice that. And then you click the button, and you capture that request. So like from an attack perspective, essentially what we do is every n minutes, because almost all web authentication challenges are timed, we're going to just keep triggering that challenge over and over and over again and push it down to the browser and wait for the user to actually go and visit the website and then click their way through. And then we'll capture their challenge. Someone also pointed out to me that, hey, why don't you just be really aggressive and make every single tab they have open that challenge until they click the button? I bet that would work too, to be honest. But the whole point of this is to maybe be stealthy. In general, though, doesn't matter. Still effective. That lives in the paint bucket folder within the repository. I called it that because if the first paint bucket doesn't headshot you, the second one absolutely will. And that's our mechanism for secretly coercing targets into answering web authentication challenges. So the final piece we have is we RDP into the target via socks, which we've kind of already covered, and then we're good. And let me just show you what that actually looks like, because I know I've been kind of rushing through this, and it's easy for things to fall on the floor, but I find that visualizing this can quickly make it clear what's actually happening. So here we're on a Windows 10 machine with a standard Chrome install, and I'm about to trigger the side load. So side load has been triggered. Now we've got our extension loaded. It's triggered developer mode for the browser. And I've also silently launched a second instance of Chrome, which is just restarting a couple of times now because at the time I didn't know the right way to run isolated web apps without triggering a bunch of restarts. But essentially, we have our normal Chrome instance with the user's default profile, and we have a second Chrome instance, which is running that isolated web app using the command line argument. And so now we're going to flip over to what it looks like from the attacker perspective. This is just this is in the battle plan folder within the repository. It's just a vibe coded HTML page, which interacts with the WebSocket that everything's calling back to. And the first thing that I did, because you have to demonstrate that you have the ability to pop calc. That's how all exploits work. Everybody knows that. Not that this is an exploit, but hey, look, we can pop calc. That's great. But that's not really the dangerous part of attacking Chrome. In my opinion, this is the dangerous part, which is our ability to sort of spy on the user as they interact with password forms or any creds. So we can capture that Git login without problem. It's not real. Here's something a little more real. This is our user Harry logging into Okta, and he's using his super secret password. We'll deal with that in a moment, but we can see that we've captured his password. So we've got Wet Bandits Forever, and now we could start logging into Okta as Harry. So separately, we're going to try to log into that internal vault, which we can't until we're tunneling through his browser because we need his network position to hit that internal resource. So this is now being SOX proxied through his browser. All this network traffic is coming from Chrome. And then, of course, we can trigger that Okta login. So this would also be coming from his address, so it wouldn't necessarily cause any concerns. We can use his credentials because we just captured them. So this is the Wet Bandits Forever password that we just jacked. And then, of course, once again, MFA to the rescue, except we're now going to run a Python script, which I'd written, which essentially takes those creds, logs into Okta, gets the MFA challenge, and then pushes it down to the browser. So meanwhile, if our targeted user is taking a look at anything that involves touching a YubiKey, so this is not Okta, this is just a YubiCode demo site. In the background, I've opened that request for Okta. They don't realize it, so they're just clicking their Titan key or their YubiKey or whatever. And now they've signed that request for us, which then, because of how Okta works, in this case, the way I've designed it, I got back a client token, which I could use to log into Vault. This would obviously be different for each, targeted resource, but still funky and effective. So within Vault, we start taking a look at the secrets. Silver Tuna is a deep cut reference for all people on this call that have seen Home Alone and remember that. That gives us the credentials that we need to RDP into our final target. We're going to force that through the SOCKS 5 proxy running out of the isolated web application using a domain of 7 kingdoms. This is just a default game of Active Directory install. Super secret password of password. That gives us access to the machine. This is all being tunneled through Chrome. And then just to demonstrate the speed is reasonable, because this is actually going to AWS and then back into Chrome. But it doesn't matter. We're able to RDP. We're able to interact with things. And we're able to capture our flag. And this could represent any amount of information or domain admin or whatever targets we really have. But end of the day, that's what it looks like to take a combination of a malicious extension and isolated web app and then sort of run amok. And obviously this isn't perfect. Edge and Chrome have different implementation details. They're not the same. So for example, unrestricted web USB doesn't exist in Edge, as far as I'm aware. That is Chrome only. In fact, until recently, Edge didn't even load isolated web apps. If you did that, it used to trigger an infinite loop and open Windows until it crashed. But a couple weeks ago or a couple months ago at this point, that changed. And now you can sideload into Edge perfectly fine. IWAs are constantly changing. I noticed the permission set has already changed. There's a policy which is being rolled out now to let you say only allow certain whitelisted isolated web apps. I think that's currently only on Chromebooks, but I'm hopeful that that will get pushed out to the rest of the browser space, because right now there's no other way to disable isolated web apps. In general, some of the permissions that I've seen, I couldn't get working, but I'm assuming that there will be more permissions added to IWAs if they grow in popularity, which I hope they do, because I think it's a really cool feature to have in the browser. And then finally, the sideloading code is actually Mac OS and Windows now. I've added code for that. Mac OS is way more unstable, but it does work. And what I recommend to defenders here is disable Chrome extensions using enterprise browser policy. What I will recommend as soon as I can is the isolated web app whitelist policy, because that will then allow people to block mechanisms or block IWAs except for what they allow. However, that's just a flag right now. There's no policy you can handle with that. Separately, I am aware of ways that you can bypass the block lists, which I'll happily talk about at question time if anyone's curious about that. So, as a secondary mechanism, people need to watch for anything that's not Chrome editing the secure preferences or local state or level DB files, or watching for those, native messaging artifacts like registry entry modifications and whatnot. And anyways, that's the actual talk itself. I'm happy to dive into questions that folks may have. I'd love to chat with you guys. There is literally no one else on earth who's going to know more about this than you folks. So
sounds good. Thanks, Michael. I will stop recording and then we can get into questions.
Heck yeah.